All right. Hey, Al, we are continuing 2C.3 notes, I believe. It was brought to my attention that we did not complete this. So on example number 3, it has you sketching the parent function log base 2 of x. So the first thing you should always do when you think about um, a graph is creating a table. So for log base 2 of x, I've created the table with log base 2 using 1, 2, 4, and 8 because 2 of x. These are going to be your smallest values of that table of the function. So I create those table and then I plotted the points. That's my blue function. And then now I'm going to describe what's happening. So if I have g of x equals negative log base 2 of x, translated f of x, what happened? Well, my a transformation variable is negative. So that means it was reflected. F of x was reflected across the x-axis. That's just a simple reflection across the x-axis, as you can see here. And what's the rule that takes place? In order for it to reflect, that means my x's stay the same and my y's become their opposites. I multiply every y by -1. So when you look at the table here, I'm still 1, 2, 4, 8 was not touched. However, my y values became 0, -1, -2, and -3. So when you describe the domain and range, your domain is still the same for each. Your range is still the same for each. What's different here is your concavity. So it's increasing. My rate of change is positive for my original function. It was concave down. And so therefore my rate of change is decreasing. And my intercept was at 1, 0. And my vertical velocity was at x equals 0. Everything's the same except the fact that I'm decreasing. My rate of change is negative. I'm concaved up, which means my rate of change is increasing. Okay. So that's your 3. So let's look at 4. So in example 4, it says, given the function, determine the asymptotes and behaviors, use limit notation. So this time, notice we're not looking at the graph. We're strictly looking at the function. Okay. So when we have x minus 1, we know that x minus 1 has to be greater than 0. Because x minus 1 has to be greater than 0, there's a boundary line, a border that we can go to. So because x minus 1 has to be greater than 0, we know that x equals 1 is our vertical asymptote. Okay. And the function wasn't reflected or anything or translated. So it's right of the vertical asymptote is increasing. So we know as the limit as x goes to 1 on the right, so heading to the left as much as we could, y equals -infinity. It's just getting smaller, smaller, smaller as we head towards +1. The limit as x goes to +infinity, going forever to the right, y equals infinity. So that's describing our end behavior. Okay. Here we have y equals log 2 minus x. So again, your restriction is this has to be greater than 0. So x cannot equal 2 because that's where our vertical asymptote would lie. Okay. But x is now negative. So our function has now reflected across the y equals x. The y-axis, not y equals x, the y-axis. So because of this reflection, this negative x, and being reflected across the y-axis, we're now on the left side of our vertical asymptote and we're decreasing. So we were doing a number like, and now we're going the other way. So now reading graphs from left to right, we are decreasing heading towards our vertical asymptote. So starting with our left-handed limit, the limit as x goes to -infinity, y equals +infinity. The limit as y goes, as the limit as x goes to 2 from the left, my y values are decreasing. So it's heading towards y equals -infinity. All right, so several things have taken place here. First, we're going to acknowledge our vertical asymptote. So our vertical asymptote is based off what x cannot equal on the inside our argument here. So x cannot be -4. Therefore, there's a vertical asymptote at x equals -4. Okay. The next thing that takes place is that we are shifted. This 2 is just going to shift us up 2 units. And then we are now reflected across the x-axis. Because we're reflected across the x-axis, instead of being an increasing on the right-hand side of our vertical asymptote, we're now decreasing on the right-hand side of our vertical asymptote. Okay. So our limit from the left, our left-hand limit is as the limit as x goes to negative infinity on the right, because we're on the right side of our vertical asymptote, y equals positive infinity now. And that's because we are reflected and it's going upwards. Our limit on the right-hand side, as x goes to positive infinity, y equals negative infinity, okay? Here, notice that my argument has nothing being added, subtracted to it. So therefore, my vertical asymptote is still at x equals 0. This -3 tells me that my function shifted down 3 units. Because of this shift, it doesn't have any impact on our asymptote or anything. It's just shifting the graph down. So we're still right of our vertical asymptote and we're still increasing, right? Still to the right and increasing. So describing our left-hand behavior, the limit as x goes to 0 on the right-hand side, y equals negative infinity. And the limit as x goes to positive infinity, our right in behavior, y equals positive infinity, okay? This is an example of what's you're expected to be able to do on a non-calculator part of the test. All right, here we're going to be analyzing whether the function is exponential or if it is logarithmic. Well, I'm sorry, if not exponential, logarithmic. If it's increasing or decreasing. So first I'm going to look at my x's. As my x values increase, my y values are also increasing, okay? Notice here, though, at my end behavior, what's happening around my values, what's happening with my x values. So this is 1.01. So as my function is getting closer to 1, is going down to negative infinity. So that lets me know that there is a vertical asymptote at x equals 1. All right, so that's the first thing I acknowledge. As I head towards the right-hand side of my function, how large it gets, it's gradually increasing, not rapidly, it's gradually increasing. So it's going to go this way. And now I'm going to describe the behavior that's taking place. F of x is increasing. Therefore, the rate of change is positive. So my rate of change is positive, greater than 0. It is concave down. So my rate of change is positive, but it's decreasing, okay? It's changing, but not as quickly. Excuse me. All right, my domain is from 1 to 0. On this one, looking at analyzing the left-hand behavior. So on my left hand, I am approaching -2. I'm getting closer to -2. As I'm getting closer to -2, my numbers appear to be getting larger. So as it gets closer to -2, my numbers are still growing. So I'm going to assume that my vertical asymptote is at x equals -2. As it goes forever closer and closer to the right, 500 is getting smaller. So that lets me know that my function is decreasing as it's going to, as x goes to positive infinity. So when I describe the behavior, I can say that g of x is now decreasing. And then, and therefore, the rate of change is negative because it's decreasing. It is concaved up. So this concaved up. So the rate of change is increasing. Okay. My domain here is from my boundary line of -2 and going to infinity. Okay. So we have a real world problem to look at. A principal invested at 6.6 and 0.25% is compounded continuously and increases to the amount k times the original principal after 2 years, where t equals the natural log of k divided by 625 10,000ths. So this would be obviously a calculator problem. Why? It's giving you a function to evaluate, especially function with decimals. So it wants you to complete the table. So evaluating these, the k value and telling you how long it's going to take. So if k represents your time, so after 1 year, after 2 years, after 4, after 6, after 8, what's happening? So at about 11 and 900 years, the investment will double. So it asks, when will it take to double? Well, this is my double when k is k double the amount. So it's going to take about 11 years for that to take place. So then we would create a graph from using our graphing utility again, because this would be a calculator problem. And then now it says, suppose you had $1,000 to invest. Your function for the amount in the account at any time t would be a of t equals 1,000 e to the 0.0625t. Use the function to verify your answer in part A. Okay. So it's telling me that if I had $1,000 to invest and I want to double that investment, we're saying that it takes about 11 years and 11.09 years. So to test out that theory, we're going to substitute 11.09 in, use the calculator to calculate, and we get that after 11.09 years, your investment will be roughly $1,999.96, which in fact is almost double your investment. Okay. And that's how you would do that. So that concludes our 2C.3.